Thanks, and thanks for being here. I mean, it's nice to be among friends as well as new people talking about current work. I'm just drafting the paper. It's not published like the previous one, unfortunately, and it's a collaboration with Maria Durban, who is a professor at the University Carlos III in Madrid, in Spain. So it's, I think, just yesterday evening while compiling the talk, I thought the first time I thought about that, and I think it was in Odense, long time ago. The first time I was sketching the equations was in the kitchen in Odense with Jose Manuel and Pancho at that time. But then he just faded away, and just last year I came again to that idea of trying to see how we could simultaneously estimate, and Jim probably was there, Jim, when simultaneously estimate different cause of death by keeping the coherence, and I will talk about what I mean for coherence. I don't need to give in this audience much of motivation, but as you will know that the overall mortality trends are a summation of cause-specific mortality experiences, and why we need to model that, because then they will allow us to recognize the drivers for the main drivers for all cause mortality, as well as probably identify health challenges, though we will see that we will stop in 2018 in our data, and therefore we couldn't identify, and we didn't plan to identify COVID when using this data. For a long time, there was a sort of like cap on this kind of research, because there was some early work saying that actually you will have a lot of drawbacks by trying to project a cause-specific mortality by cause of death. So in the research, in the demographic community, there was a sort of taboo on this, so we wouldn't do that. It's bad. But then later, there were like, then these are like just two recent developments trying to use cause-specific mortality simultaneously to forecast overall mortality and to forecast cause-specific mortality at the same time. The work, like the seminal work by Jim on CODA, that wasn't finally applied to cause-specific mortality yet, but in specific causes, and here is the reference, or other kind of Bayesian hierarchical model trying to forecast cause-specific rates in geographical subunits, but with many other issues that I won't go through now. So these are just simple introductory slides for giving you the idea on why, even though you may wonder why. And then go directly to the kind of data structure that we have. You could imagine that when we work with mortality data, I'm not thinking about additional covariance information and things like that. So we have only a set of three-dimensional. We have three-dimensional arrays of death and exposure over age groups, years, and then the layers are the different cause of death. In this talk, we will talk about only US data from the human cause-specific cause of death database, but we have done other application, and we plan to do it for many other populations. And actually, we just group our data, our cause of death in big groups to make it simple in terms of, or easy of presentation more than for computational purposes. And then, as I say, we have classified by age, year, and cause of death. And then what we do, we add the final layer in our exposure, in our death, our Y, I call it Y to death, because it's our response in statistical terms, and exposure at the E, as a final layer, the total number of deaths. So I have a complete data set that, of course, it looks like a nuisance layer, but it will help us to keep the coherence I will talk about. And of course, if we don't have any model and if we don't specify any kind of distribution over age and time and cause of death, that's the best optimal maximum likelihood estimation for mortality would be just to compute the cause-specific and age, cause, and year-specific death rates as well. So, and then one additional feature of this kind of data is that actually we are in the competing risk setting. So basically each layer has exactly the same exposure, and then people are exposed to die by different cause of death. So just to have a look at the data, here are for US, the one I will use it, males, we don't see too much the trends because we use a common axis, but you clearly see in the infectious and respiratory disease, the HIV pandemic in the 80s, early 90s, and the recover afterward, some other spots, some for external cause, you don't see too much, but there was a small increase in the last years for US males, and we have the total there. So these are the kind of data, but these are just, as I told you, the rates, so the ratio between the death and exposure for each age, time, and cause. What we actually model are the number of deaths, because this is the actual random variable when we deal with mortality. And here you see a bit more the difference in terms of size and importance of each cause, as well as possible cohort patterns due to different cohort sizes. But of course, then we will use the exposure over age and time, and that will take care of that as an offset. When I talk about coherence in this case, I don't talk about anything more than just say, I want to model this death, taking into account the exposure for each age, year, and cause, with the constraint that actually the sum of the death for each cause should be equal to the overall mortality, to the overall number of deaths. Of course, within the model, not in terms of actual data, because in terms of actual data, this is already defined by construction. So in terms of modeling, the stochastic assumption is the classic one. We think that each the number of deaths within each age, time, and cause is Poisson distributed with a certain force of mortality that multiply the common exposure. And the force of mortality is expressed in this way. So in the log scale, of course, we have used the log link as in the classic GLM, and the log mortality is the product of the model matrix and coefficients. Okay, that's how, if you see it like that, that's a GLM. And how they look, this B matrix. This B matrix is a block diagonal matrix where within each block we have the Kronecker product of B splines over age and over time, over A and over T. And just to give you a representation of one of them, this is how it will look. Of course, we will use many of these hills. So it will be a really dense carton, egg carton for each of the cause of death. Of course, if we do that, then we have no connection between one cause of death and the other one. We could have just independently fit each cause of death in a classic two-dimensional GLM model where the B-splines are our regressors. But we want to have this constraint at the death count level. Remember, we don't want that at any other level than death. So we can write it down, this additional constraint. Is basically that the C matrix multiplied by what we expect in terms of death. What we expect in terms of death is the product between the exposure and the force of mortality, image that in the vectorized format. And what is the force of mortality in our model? The force of mortality is the exponential of the product between the B and the alpha. And that says to sum up to 0. Why sum up to 0? Because actually how the C matrix looks like is nothing but the canonical product of identity matrix over age and time. These are over time and age, and then multiplied by this C matrix that takes basically the depth for each cause, and then subtract the final layer that is the total. Okay, so in this case, what we do, if we obey this kind of constraint, then we are somehow forcing the sum of the depth for each cause to be equal to the total one. And well, it's immediately you can see that the C matrix can be written as a canonical product. We have seen before that actually our basis can be written as a canonical product, and that has all the, it's a great advantage because actually we can embed all the inner operators within the generalized linear array model proposed by Carlo et al. In 2006 with a lot of computational advantages in terms of storage and time. So up to here, what we have, if we forgot about the constraint, we have a simple GLM with basis made out of B-splines. We have a constraint that actually has some issues that we will see then later, because what we see immediately is that the constraint is not a linear combination of our coefficients. If there was a linear combination of our coefficient, that's the exponential here. It's not a C multiplied by alpha. There is that exponential there because we want the constraint at the depth level. So we have like a model that is a GLM, and it will be nonlinear because we will use the P-spline approach with a nonlinear constraint. And so plain Lagrange multiplier cannot be applied here. For those who are wondering what the problem here is. So, but at the same time, even before going to that, what we have many coefficients because we use a really dense B-splines over age and time, and then for each cause of death and for the total. But then we have all possible age and time constraints. And that's, in France, they say, yeah, in English, you say you cannot have the cake and eat it. So that leads to singularity problem because you have more actually constrained than coefficients, and that's a big problem. So what we want that for each dot, the sum has to be equal to the total. So image that really dense constraint that we want, but we want also something that is going over age and time in a smooth way. So we run into the problem. So we have too much flexibility, if you want, with a big constraint. So what we do it, we need the compromise between the number of coefficients, the number of alphas, and the number of constraints. So what we propose here that we keep a rich basis over age and time so that we get a really good data description, but then we somehow give a bit, not less importance, but let's say like we reduce the number of dense constraint that we have here, and that what we decide that we enforce the constraint over equally spaced data points. And we assume that within each data point, then the smoothness behavior of the final fit will take care of the constraint within it. And I can tell you it works really well, and we will see the result later. In terms of equations, the difference is that actually now we don't have the C matrix. Remember the 1, 1, 1, 1, 1, minus 1 that multiplies the identity matrix, but it will multiply this kind of, we call it still C, which is the canonical product of the less dense number of constraints we have over age and time. And that you get rid of the identificability problem if you want, the singularity. So how we would estimate that model? Well, I'm in a frequentist approach. If you don't have constraint and you don't have anything else that actually the B matrix I show you, that's basically a Poisson likelihood that you could maximize. But then what we do it, if we use many B-splines over age and time, as you could guess, we get really fluctuating outcomes. So what we do, we just penalize the coefficients. So we don't choose the number of B-splines, we just penalize the coefficient in the classic B-spline approach, and actually, as well as the B matrix as a structure, block diagonal structure, also the P matrix will have a block diagonal structure. Because we want to smooth over age and time, we don't want to smooth over causes. And what we do, you could imagine that we have smoothing parameter over age and time for each cause, and that is a really huge optimizational problem. So what we decide, that we decide to optimize for each cause independently the lambdas, the smoothing parameter, the amount of smoothness over age and time, and then we use them for fitting the overall model with the constraint. Because actually, if we have only these things, that would be just an independent fit for each of the causes. We want the constraint there to ensure the summation of the depth to be equal to the total. And that's how we do it. We enforce this constraint using Lagrange multiplier that cannot be used straightforwardly, as we will show in the next slides. But this is how you would normally have in a classic statistical framework, how you would impose constraint within a model. You just have the Lagrange multiplier multiplied by your constraint that has to be equal to 0. Remember that I wrote it to be equal to 0 because then it could be included directly in this way in my penalized constraint Poisson likelihood. So that's what it is. The problem is that if you work it out the derivative, the first and second derivative with respect to alpha and with respect to the omega, then you can immediately see that actually the constraints are non-linear, and here could cause some problem. So you cannot use the classic GLM framework in this case with linear constraint. So you have to work a bit the estimation procedure by hand. And here I give you just a slide for those who like equation. If you do the first and the second derivative with respect and the partial derivative with respect to alpha and the omega, that's the scoring algorithm you will find out. It looks pretty complex, but if you imagine that actually, if you forgot about the constraint, that's basically the classic iteratively weighted least square with a penalty that is used for fitting the generalized linear model with these splines as a regression. So what we have on the top of that, you have this kind of things that needs to be updated exactly like for the alpha in terms of omega. So you have to do it iterations, not only to update the alpha, so the smoothness over age and time for each cause, but also to force the constraint. And there is just the outcome in terms of fitting in 2000. So you could, this is the fitted cause-specific number of deaths for each of the cause over age groups. This is, and then just to show you that actually these are the fitted total, which are exactly like, even though we do not force for each age, remember it's less dense, but anyway it works for each of the age groups, and it works also for each of the years. Of course, up to here we are just working on the observed data. What we need to do it is to forecast. And so what we do it, we think about forecasting as a missing value problem. We say we are nothing about the future, so we just put a 0 there. And so we augment. If you think about a single cause, that's the classic P-spline approach, then you will augment the exposure and the death. And then you will set up a weight matrix, which is equal to 1 for the data where are observed and equal to 0 for the future. Okay, this is the weight matrix down there. And what you do, you augment also your basis, okay, over the time dimension, because there is where you want to forecast. And then that's simple because if you have a weight 0, 1, you are still in the classic regression setting. That's the advantage of keeping all the tools from the regression setting, because then you can put an additional weight matrix in your algorithm and everything works. Of course, if you have to do it for multiple codes, that's what you have to do. You have to augment each of these layers. And of course, you have to create an additional array, which is equal to 1 for the data observed and 0 for all the parts that are not observed. So it's not an augmentation in 2 dimensions, but an augmentation in 3 dimensions. The only issue here is that actually you cannot put any arbitrary number for the depth in the future, but they need to comply constraint, in the sense that actually the number that I put for cardiovascular, I can put like 1 everywhere for cardiovascular as an arbitrary number, 1 for neoplants, 1 for external, 1 for the infectious, 1 for the other disease. Then I need to put 5 for the total, but it can be any number. They just need to obey the comply the constraint, but they can be any number. You want to have the constraint in the future, but actually you will never know the number of deaths because you don't have the exposure for the future. So it's obey at the death level, but even though the final outcome is only at the mortality rates level for the forecast. So, and of course, what you do, you also augment each of the hectaton for each of the cause of death. Once you have that, then it's basically the same kind of exercise that we had before. So if we would have done that, we would have obtained a nice constraint for the future, the smooth over age and time. But then there are some issues in terms of regularities, in terms of structure, that we actually, by doing so, what we are doing, we are just treating death and exposure as they were numbers. There is no demography up to here. There is no demography at all within that system. So, and what we have done with Maria, we try to, combine this kind of approach with the previous approach I've done for a single cause of death, so that we could guide the statistics with demographic knowledge. So let's have a look for what could happen if we see and try to capture regularities in mortality over age and time for a specific cause of death, in this case for the total. Okay, so in here what you see is the actual and smooth mortality rates over age and time here, and here are plotted over age for different point in time. These are the typical shape of mortality over age. We all know that. And this kind of regularities, the feature of this kind of a pattern, where could be seen without looking at the level? Well, it could be just seen by doing the derivative of these curves. If we do the derivative of these curves, what you see here, you immediately see that actually what in demography people call rate of aging or life table aging rate, anyway, is the first derivative of the log mortality over age. And since we are smoothing, it can be done in the continuous framework. So, and is basically giving you all the information about the structure of mortality. If you take the 95% confidence interval of this, it's basically telling you what the mortality is without taking care of the level. And this is something that we want to be in the model. We want to inform the model about that, because we know that mortality cannot be like that. It has to be in that derivative. It can be at a different level, but the shape we know has to be there. Of course, you can do the same exercise for different ages over time. So in this case, what you see here are the time trends of mortality for different ages. And here is what I call rate of change, the derivative over time, in this case, of the log mortality. Well, just for those who are more, from demography, just coming back, This is basically the B of the Gompers in a continuous framework. Okay, that's where, at least for these data, is. If there is no heterogeneity, but let's say if you fit the Gompers there, then you will have just a single line. So, and here what you see the trends over time and the derivatives. And what you see here, that even small changes over time, they really like completely are disproportionate in terms of rate of change. You have always to remember that whenever you compute the derivative of any curve, you will obtain always something that is less smooth than the curve itself. That's a classic issue in statistics. So if we do so, and let's take 3 ages like that, then you see that small change really like exacerbates in terms of relative derivatives. So let's have a look at this 3 age in focus on them. You see here the typical situation that we have in the 80s. It's saying like that if you are in the positive, mortality is increasing, and if you are in the negative, then mortality is decreasing. You see that for age group 60-65, mortality is mainly decreasing, but in the last years, and therefore the derivative goes to a positive side. And here you see a sort of stagnation around 0, then mortality is decreasing, and then you go to the negative side. So that gives you the feature of this data of these ages over time. And we want actually this feature to be within the model. We want to inform the model about this feature. Otherwise, there are only data. There is no demography in it. But instead of taking the 95% confidence interval, at least in that paper, I propose to take only the interquartile range, at least for the rate of change. That's just one of the main options you could have. And what that means that at least for these 3 ages, we only care about these dots here. We forgot about the big jumps that we have seen in the past. And we want to inform the future only about these dots, not about these big jumps. Of course, you could change that, and that's the user can adapt and can be different for each age. It's not a problem at all. So if we take only the interquartile range, that's what you will get for these 3 ages. So basically for age 35, 40, you allow to be increasing mortality or decreasing mortality at the same time. For age 60, 65, you somehow want the model to know that in the future it can only decrease. And for 90, 95, you just say that it should mainly decrease, but it could actually also increase. So you could imagine this as a sort of prior in your model. And of course, you can do that for each of the age. And of course, since we are working for each of the, so this is the rate of aging, what I call the rate of aging, and this is the rate of change for each of the age. So we want that the future has to be within that. But actually what we know, we are not working only on overall mortality, we are working on different cause mortality, cause-specific mortality, and this is what you have seen before, and this is the same for each of the cause over age and time. The rates, you see the differences, but what we want to see the feature of these surfaces. So we do exactly the same exercise. We calculate cause-specific rate of aging for each of these cause, and this is the 95% confidence interval. This is what you have seen before, and these are some of patterns, the cause-specific patterns in mortality. And you see that for external cause of death, there was a stagnation. Then there was basically an increasing mortality in the last period. You see an increasing mortality in the infections and respiratory disease with much more variability in the first period, in the first ages. That comes from the HIV. You see a neoplasm that is basically was improving a lot in the first years, but now not anymore. Cardiovascular disease, always an improvement over time for each of the age. And of course, you can do the same exercise by looking at the rate of change for each of these cause of death. And here you immediately see the the HIV pandemic as well as the recovery in the 90s. And here it is the rate of change. So for each of the age, this is what you have seen before for the overall mortality. And here you see what you in terms of rate of change for each of the age in each of the posts. So now we want to inform the model about that. So disregarding this shape seems unreasonable. We want demography to be within our model. So we just say that the future mortality must follow this age profile and rate of change for each of the posts. So what we do, we use an approach that is called asymmetric penalty. So we have an additional penalty in the system of equation that you see before, in which iteratively in the future, it just say whenever you go outside in terms of derivative from what I inform you, go in. So it's a sort of like, it's called asymmetrically because actually it's working only when it's needed. And it needs to be iteratively estimated every time. Not iteratively estimated. You don't estimate anything. You want that the alpha so that the derivative is within the confidence interval. And this has been proposed for one single cause a few years ago in a paper in demographic research. And what we do now, we just generalize this approach within the 3D setting that you have seen before. So we have additional asymmetric penalties for each of the cause of death. And here is the result for different age groups. So what you see here for different age group, the overall mortality, the fit, and the forecast with the confidence bands that actually being in a regression setting can be computed analytically, automatically from the variance covariance matrix. And in gray, you see what the results that you would obtain if you fit each cause of death independently with the shape constraint I showed you before. And in color, you see the outcomes when you force the past and the future number of deaths for each cause to be equal to the overall number of deaths. So we can discuss about the outcome and but one way of seeing one single value for the outcome is to just look at the life expectancy at age 30 because we started at age 30 and you see that actually if you have the summation constraint or not for the previous years, it doesn't matter at all. So it doesn't change the outcome. But when you go to the future, then it's true you have a bit pessimistic, more pessimistic. It's the case of United States, but we didn't check whether it's a common feature or it can be different. We didn't force to be pessimistic. It's just out of the data. When we actually additional to the shape constraint, we impose the summation constraint. Okay, we impose that actually this is the total mortality, but actually what we are estimating here is the overall each cause specific mortality. So, and if we do so, but what we found also really interesting is that actually if we incorporate the confidence interval around these two extrapolated life expectancy confidence interval that can be computed by delta method from the variance covariance matrix, then you will see that when you include summation, you are more sure about the future. Because you have actually, and that qualitatively you could think, you have actually add additional information coming from each of the goals. And so by adding more information, you somehow are more sure of what would go on into the future. And that, I think, has a lot of advantage from many points of view. So just to conclude, what we have just few remarks. So we smooth forecast cause-specific and overall mortality simultaneously. We don't need to decide a specific reference or anything like that. Everything is done in one go. What we have a non-linear summation constraint, but we have shown how to incorporate this using Lagrange multipliers. The scoring algorithm has can be embedded in the GLAM framework with great advantage. And then for US, at least in terms of outcomes, we have seen a more pessimistic trends, but with narrower confidence interval. For the future, of course, we are thinking about how can we actually put it in low priority, this first point. So how we can select the 2 by k plus 1 smoothing parameter, because if you have 5 cause of death, we have 12 smoothing parameter to optimize over age and time for each of the cause and the total. And that's a huge issue. But what we have tested for small sample sizes, for small area and so on, that it doesn't matter if we optimize individually, independently each cause of death, and then we use this smoothing parameter in the overall system. Also because then there are symmetric constraints that keep things really within what we expect. Of course, we still didn't do any back testing for model performance, and we are thinking about extending the model for male and female and for regional mortality settings, though the issue there is that actually the exposure is not the same like in the case of the cause-specific mortality, so the layer of exposure is not the same everywhere. And something that we are actually working on, and I didn't put here, is how to incorporate these. You have seen that we are working on age group data, but most of the time our outcomes are needed at single year of age. So how can we use what is called a composite link model within this framework? Of course, the issue is not to do it. I have done already. The point is that I still didn't do in the GLAB setting. And it would be like methodologically a great advantage to have, regardless this problem, a CLM within the GLAM setting, because that's something that hasn't been done. And we are just using this application to do that kind of advancement. So thank you very much. And if you have any question, I will be more than welcome to answer. I hope I wasn't done. I didn't check.
Thanks a lot for your presentation. We have comments, questions.
Yeah.
If I may start, I have 3 questions. So maybe just I'm going to ask them one at a time.
Yeah.
The first one is very simple. So I think it's a great finding that you do not need to put this constraint that the sum of the parts should be equal to the total in terms of deaths, like for all data points, but just picking up a step.
Yeah.
Do you pick this step at random, or have you tried, like, how did you arrive exactly at this step? And is there some algorithm how to optimize it so that you don't, like the question you asked to Germans, like, is there a way to optimize the number of data points you need to impose this constraint on?
We didn't optimize. What we've done now, you could imagine that actually the more points you put there, the more flexibility you need from the lambda. And so you will get some weekly outcomes. So what we do we just say, like, we put as many as we can until we don't get a singularity problem. Yeah. So at least in this exercise, we put every 5 data points. And what we have decided that we also put, like, we somehow nail the corner, so that otherwise if you put only internal constraint, then at the end things can go a bit wild at the edge. So we just nail at the corner. You can see here in this here. So we just say, like, we nailed that. Okay. So that for sure up to the end we go to the constraint. But at the moment it's pretty. We don't put many, mainly because then if you put many, then you ended up having a really weird pattern in terms of mortality, meaning like that the BAC is not able to select properly the the constraint. So let's say let's do like the other way around. We select the BAC independently for each cause, and given the selected lambdas, we put as many constraints as possible. That's what we do.
Okay.
Yeah.
Thank you. My second question is regarding the rates of improvement in age-specific mortality. So there are different ways how to calculate them. So did I understand correctly that you smooth the data and you just take the derivatives and then?
Yes, I take it. If you would have compute rate of aging or rate of change from the original observed data, you will have really like big jumps. So you need to smooth them. So what we have done, we smooth in a simple two-dimensional B-spline, and which has an advantage when you want to go in terms of derivatives, because once you have the fitted alphas, then you have just to you have automatically the derivatives by multiplying these alphas by the differences of the B-splines. So you have exactly like you see, you can express the log mortality as B multiplied by alpha. You can express the derivative of the log mortality by H multiplied by alpha. So you have it already, and you can construct it outside.
What are you doing at the ends where the B-splines are not fitting very well?
They are not fitting. No.
Or they are.
They are.
Okay.
There is no edge issue in the. That's one of the advantage of the B-splines with respect to kernel and other kinds of smoothing.
Yeah, and in relation to these improvements, you're including the information about AIDS. So you are projecting that
eventually.
In a way, yeah, you're projecting that this might happen in the future. So is there a way that you isolate this and just have an estimate of these age-specific mortality improvements in the absence of?
I haven't done the exercise, but like these are information I get from the data once you smooth that, and this is typical. You say like you see in this even though you take only the interquartile range, actually you allow the future to have AIDS and to recover from AIDS. Basically, it's not AIDS; it could be anything else. But what you say, like if you think that for these ages that's improbable for the future, then you cut here and here. And then you say, these are no, like you can play with these things as much as you want. I had big issues is when I submit this paper and try to get this paper out, because people think that that's a big problem, because you need to think about it. But my idea is that actually that's a big advantage, because it gives flexibility to the forecast to decide what they want. If we want interquartile range for these causes, but not for these ages, and then for these, if you think that if image like including in the data COVID, we want that a certain things like COVID happen into the future, yes or no, you could decide that by forcing that. If you image other kind of forecasting methodology like the Lee-Carter, what the Lee-Carter would do, would just say we force the mean of the improvement, and that with the future, the beta of the Lee-Carter. Okay. In this case, you have more flexibility. But then, if you shrink this up to the mean, then you could think it as a sort of Lee-Carter with a nonlinear trend. So yes, you could imagine that this is a generalization of the Lee-Carter, if you want, with a nonlinear trend and much more flexibility in terms of the beta x of the Lee-Carter. But you could play with these things in terms of when you have flexibility. I always say, like, flexibility comes with responsibility, and that means that you need to think about that.
I need to write it down.
And one last thing, when you showed the forecast for life expectancy, have you compared it with like CODA-based models? How?
Not yet. That's in the plan.
How close they are? Yeah.
And what I found that with CODA, I still didn't find really, but that's probably you had it, and I have to talk with Marie-Pierre for cause of that. I still didn't find neither a paper nor a a really available code for running it. So
not talking with QCM?
yeah, maybe yeah.
I'm not allowed to share. I'm sorry.
Yeah, he's not allowed to share, so I can talk, but that's all. But yes, it's and actually I saw that there is Marie-Pierre recently published an archive paper on this, but still I don't have the really available code. But that's in the plan. That's in the plan. But what I'm really like enjoying now is to see the CLN within the GLAM. That's really fantastic in terms of geometric algebras, but that's much boring from a demographic point of view. But it will solve a lot of problems, regardless of this issue of the co-specific.
Just out of curiosity. So you put constraints, yeah, only around co-specific, like age of rate of aging and rate of change. I was wondering if you check in your final estimate at the total level, where it stands in terms of total. So I mean, you force at the co-specific level to be within these bandings, but okay, you also have you also constrain the total.
Yes, yeah. What in the paper for the overall mortality checked how much is changing in terms of future life expectancy or lifespan disparities if you change, instead of taking 50%, you take 35%, or you take 80, or you take 95%. So if you make it larger and larger, these kind of things, and it depends. If you have really striking issues in the past, that could cause some problem. Like if you say like not only one part of the HIV epidemic, but if I put everything there, then you basically give too much flexibility, and that actually where the problem comes. Because if you use a simple B-spline model in 2 dimensions, you can get really wild results. That was my motivation in that paper. So like, how can I guide statistics with demographics? Yes.
My first reaction to this is like there are causes of death where when you talk to the experts, they will give you a very narrow range possible of what can happen in the future, and there are other causes of death that we don't know at all. Well, so it's on some. My usage of this will be like on some causes where we have something there. A lot of constraints, and other is like it will be very.
Yeah, that's an option. Yeah, but you have that option. That's not a problem. What actually I'm always thinking, but never have time to do it, is that at least for the overall mortality, the idea is that actually we have specific trends that are there over age and time, but there are also trends that we know there are over cohorts.
Yes.
So what we could do, we could also think that these kind of things are not fixed at all ages or over time, but they could change, and you can give more flexibility for the future. So somehow you could think that you could also say like, look, in the first 10 years has to be like that, but then later on has to be like that. You can do that. So you could make it more, let's say, flexible in the longer horizon when you forecast. That's another option. Yes.
I have a question about your Poisson assumption at the beginning.
Yes.
Will it work with other distribution, like maybe binomial, or if you would use like multivariate Poisson with common factors?
Yeah. This one you mean, like here?
Yeah.
We didn't try that. What we have to bear in mind is that actually, at least in 1D case, without any constraint and anything, that has been done, and it's already in the package, mortality smooth. But instead of using a negative binomial, what I do I use a sort of pseudo Poisson, in terms that I re-optimize the smoothing parameter according to the amount of over dispersion I have. because that with respect to a simple GLM, let's think about like basic one. Simple GLM, when you have a fixed number of coefficients, the adding or no over dispersion will lead only to an augmentation of your confidence interval. So you are less sure about what you see. And therefore, what you get exactly the same fit estimate, point estimate, but larger confidence bands. When you move to a nonlinear world with B-spline or any kind of nonlinear smoother, then what you have larger confidence interval, exactly. But then if you are less sure about your data because you have an extra Poisson variability, then you smooth more your data because you believe more on your model than on your data. So yes, a sort of outcomes not only in terms of uncertainty, but also in terms of amount of smoothness. And the direction is that the more over dispersion, the smoother will be your data. I didn't try in this framework, but I imagine that if I do that in including over dispersion, then I get smoother outcome. That could be done. For example, you could think that for the past you want to include over dispersion. That means that you have much smoother rate of aging and rate of change. And that has a consequence in your future. And then you can keep, I think for the future, it doesn't matter much. But then in terms of what you decide, what is the observed rate of aging and observed rate of change, then has some meaning testing different distribution. That's distributional assumption.
Follow up on this question. Can you forecast proportions? Is binomial?
Yeah, like instead of having the Poisson, you have the binomial here. And then instead of having rate, you have probabilities. Yeah, could be done. I haven't tested that. My idea is that actually it depends on the data structure you have. So if you think about Alexis diagram, if you have squares, these are rates. So you have the number of deaths and exposure. If you are in the parallelogram, so you have the people at risk and the number of deaths, then this is a binomial. So most of the time I use the square and therefore I go for the Poisson. But you know, like the difference will be if I go to the equations for of course you will have a different equation here. This part won't change at all. Yeah, probably the only change will be here. You will have an anti-logic here instead of having the exponential, because here what you have the inverse of your link function. This will change with the binomial, but still you are in the GLM framework. You have to rewrite these things here. This will be different because it's not Poisson, it's binomial. Let me think. Here there will be the anti-logic. The rest should be the same. Yeah.
Good. There is any
Yes, there are
any question in the online. If not, thanks, Giancarlo.
No, thanks to you. Thanks a lot. Huh?
Let's have some final words.
Yes.
Close this.
Thanks a lot to all the presenters and all attendees here and online. I think we heard presentations from many different angles. We started from looking at the structure of causes of death and how we can identify dependencies. Then we focused on different models that try to incorporate these dependencies and estimate and predict mortality by cause of death. And today we had I would say a classic model extension presented by Giancarlo with a lot of novelty and nuances that account for better and more accurate predictions, and also to me and probably to a lot of you a revelation, the model by Germans. And I think one way or another, these types of methods will play a larger role in our estimates and predictions. So what these methods, well, do not account for is, to some extent, is causality. So they do not measure directly the effect, what Jana pointed out, the effect of certain variables on the outcome, but the way Germans responded to this, and I completely share this view, is that the structure of these, well, either regression tree algorithms or neural networks algorithms help you identify at least not the magnitude, but exactly the factors that led to the ergodic state of the system what we're looking at. So we are planning within this project to use such types of methods to study what we call in the project the paths to death. So what are like the groups of morbidities that jointly pile up together and lead to death. Yes, one more thing that the Germans demonstrated today is how lucky we are that we will get access to the Danish data, because we will be able to look not only at causes of deaths per se, but also at a number of other explanatory variables. And Cosmo has already quite some experience analyzing these data. I mean, in a non-machine learning setting, but we will have the opportunity also to compare the performance of machine learning and I would call them classic clustering methods. So yes, I think we are entering the more exciting phase of the project, where we will be able to use the individual data and well, see whether we can identify structures in causes of death and in morbidities that are having that are forming these separate paths to death. And we will be very happy if we can collaborate within this project with all the speakers and all the attendees that might be interested. So this is my take on this. I was extremely happy. Thank you once again. Thanks to the SCOR Foundation, to SCOR for your hospitality and for the great organization of this workshop. We were extremely happy to exchange ideas and to show the directions in which we're moving within this project.
Thank you very much for your kind words. And once again, SCOR Foundation is very happy to see this workshop held successfully. And this steering committee, we organize 2 workshops per year. So I think this workshop demonstrates how important is collaboration between research academics, researchers, and SCOR colleagues. So it's very important to put away, for the further orientation of the research. Within this share, I would like to how do we say, to thank all speakers, for their excellent presentation, from both sides. So how do we say, it's very, not only, well, I can say the items quite large, you know. So, and from different countries, this will come from different countries, and different methodology to calculate mortality, etc. So, we should all, how do we say, researchers, the excellent, continue the excellent works, and of course, our foundation is there to continue to support this mortality research. Thank you.
Thank you, guys.
Thank you.
Thank you, everyone.
Bye.
Thank you.
Thank you.
Thank you.
Bye.
Bye, Matthias.
Bye.
Thanks for your insightful comments. Thank you.
Thanks for letting me join in. It was super interesting. Have a nice weekend.
Thank you.
See you.
You too.
See you soon. Super.
Matthias is a professor. Okay, it's not a colleague. Okay.
Nice job. Is in Stockholm. But
Same even. So 12:30, I think, we are for lunch.
Yeah, we have 15 minutes, so but we can also go there and
Yeah.
enjoy the terrace.
yeah.
If it's not raining.
So see you.